As the next example, let us consider a reactor. The reactor is a continuous stirred tank reactor. That means it's a well-mixed reactor, and the reaction is also assumed to be isothermal. That means there are no heat or temperature effects in the system. So what happens here is there is a stream that comes into the reactor. The volumetric flow rate is denoted by the symbol Q in meter cube per minute, and the feed concentration of species A is CAF. That's the symbol, and it's pure A. That means there is nothing else in the feed stream except for species A. So the concentration of the inlet stream is denoted by the symbol CAF, and it's got the units of moles per meter cube. So to be specific, we can say it's moles of A per meter cube, right? Moles of A per meter cube. That means in 1 meter cube of that material, you will have so many moles of A being present, CAF moles of A being present. So that's the idea. And now what happens is it comes into the reactor, and there the conditions are such that the reaction A going to B takes place. And we are going to assume that the reaction is first order. That means the rate of the reaction, right, for this reaction A going to B, what is the rate at which this reaction proceeds? So the symbol for rate of the reaction is R, and because we are talking about species A, so it is denoted by the symbol RA. And since A is the reactant species and its concentration will go down because of the reaction, we indicate it with this minus. That means that convention is the reactants are often indicated by minus R to just say that it is a reactant and its concentration is going to decrease. So the rate of the reaction, right, is K times Ca. This is the rate at which the species A gets depleted or converted due to the reaction forming B. So the units of rate of the reaction is always moles per meter cube per minute. Always. Whatever be the system, the rate of the reaction is expressed in moles per meter cube per minute. Here it is about species A, and therefore we denote the rate of the reaction or the rate of disappearance of A to be moles of A per meter cube per minute. That means if I have 1 meter cube of material, this many moles of A will get converted into B every minute. That is the idea. Okay. And since it's a first order reaction, we say minus RA is proportional to CA. Okay. That means the rate of the reaction is proportional to the concentration of the species. So if the concentration is more, the reaction rate is more. If the concentration is less, the rate of disappearance of A is less. So it's proportional to Ca to the power of 1. So that is what is meant by a first order reaction. If it is a second order reaction, it will be Ca to the power of 2, for example. So just to keep things simple here, we are just going to assume it is going to be a first order reaction. We can get rid of this proportionality sign by writing minus Ra is equal to Kca, where K is the proportionality constant, also better known as reaction rate constant. Now this Ra is going to be in moles per meter cube per minute. Always the rate of the reaction is given by these units, and since we are talking about A, we can write moles of A per meter cube per minute. That's the rate of reaction always. Now that is going to be equal to K times Ca. Ca we know has units moles of A per meter cube. Therefore, K for a first order reaction alone should have units of 1 per minute or minute inverse. So for a first order reaction, K's units is 1 per minute or minute inverse. If it's a second order reaction, still minus Ra will have the units of moles of A per meter cube per minute. And now if the right hand side has got Kca squared, because it is a second order reaction, Ca squared will have the units of moles of A by meter cube whole squared, and therefore the units of K will have to be adjusted accordingly to make sure that the units of the right hand side and the left hand side are the same. So presently we will talk about first order reaction, and therefore the units of K is in minute inverse or 1 by minute. The volume of the tank contents is indicated by the symbol V, and it has got the units of meter cube. So we are assuming constant volume and constant density. Therefore, when we write the mass balance for the system, the overall mass balance for the system, it will turn out to be Q in is equal to Q out. Therefore, we are just saying the outlet stream will have the volumetric flow rate of Q, which is the same as the inlet volumetric flow rate. This is because of our assumption of constant volume and constant density. Now, the exit stream has got a concentration Ca, which is the same as the concentration of A inside the tank. As we observed in previous examples, because of the well-mixed condition of this vessel, in this case the reactor, the exit concentration will be the same as the concentration of the vessel contents. Therefore, we have the same symbol for the reactor contents as well as for the exit stream. So in a nutshell, inlet stream comes in at a flow rate of Q and its concentration is CAF, and in the vessel A gets converted into B, so the concentration of the A drops from CAF to CA when A leaves the vessel. The concentration of B at the inlet stream is 0, but because B is formed in the system, therefore B's concentration will be higher when it leaves the reactor as compared to the inlet concentration. Since we have two species here, A and B, we can write two balances, two mass balances. So we can write a mass balance for A, we can write a mass balance for B. Or we can write the overall mass balance and balance for species A or species B. We have already done the overall mass balance by saying the exit volumetric flow rate is the same as the inlet volumetric flow rate, as we have also assumed constant density. Therefore, the overall mass balance is already done. Therefore, we will write the mass balance for species A. If you write the overall mass balance and the mass balance for species A and species B, one of the equations will be redundant. So we need to write only two mass balances, either overall mass balance and one species balance or two species balances, because this is a system with two species A and B. And all I've said is we have already written the overall mass balance by assuming the same symbol here. So we'll write only the mass balance for species A. So we'll observe the system again for a time period between T and T plus delta T. The overall mass balance is done, as I've already stated. So when you're writing the balance for species A, now what we do is we are taking inventory of the moles of A present in the system at the final time. And we also take note of what was the amount of A in moles at the beginning of our observation period. So the difference between the two gives us the moles of A that has accumulated in the tank during the time interval delta T. So during the period of observation, the system has accumulated so many moles of A. And this could have happened because A came into the system through the inlet stream, A left the system through the output stream, and also because A converted into B. So there are three mechanisms that we have to take care of on the right hand side. So moles of A that entered the tank during the time interval delta T through this feed stream. So since it's an inlet stream, it brings in material A, therefore the sign for this is plus. And if it is because it is plus, we don't write it with a explicit plus sign. Now A leaves the system in two ways. One is it leaves as A itself in the exit stream. Unconverted A can leave the system. So this is what leaves the reactor via the exit stream during the time interval delta T. Now A also gets converted to B, and therefore there is a loss or consumption of A. So this is the first time we have noticed consumption term in our models. So because A is consumed, so it is kind of something like A is leaving, right? So we have a minus sign for that, and we have moles of A disappearing due to the reaction during the time interval delta t. So uh, this difference between what comes in during the time interval delta t, what leaves the reactor during the time delta t, and what gets converted to B during the time interval delta t, that is going to lead to the accumulation of moles of A between time t and t plus delta t. So now we have to convert that into symbols based on the table that we have already discussed in the previous slide. So if we want moles of A in tank at time t plus delta t, so we know that V is going to be in meter cube, concentration of A, right? In the tank, the symbol for concentration of A is Ca. Therefore, we say a meter cube is for volume, Ca is going to be in moles of A per meter cube. So V times Ca will give you moles of A, which is what we are after. We are after moles of A at time t plus delta t. So that makes sense. Why is Ca used? Because that is the concentration of A in the reaction vessel. And we are taking inventory of what is inside the reaction vessel at time t plus delta t. So the same combination of variables at time t. So this is the accumulation during the time interval delta t. And this accumulation happens because of the inlet stream, the exit stream, and the reaction term. So if you look at this, basically it is Q times CAF times delta T. CAF is used because the concentration of A in the inlet stream is denoted by the symbol CAF. Q is the volumetric flow rate in meter cube per minute. CAF is going to be in moles of A per meter cube, and delta T is going to be in minutes. So meter cube cancels with meter cube, minutes with minutes, leaving you with moles of A, which is fantastic because the left hand side has dimensions of moles of A. So this is fine. And the same combination of variables for the exit stream. Of course, the exit volumetric flow rate is Q. The exit concentration of species A is Ca and delta T, right? So we are just using the same kind of variables, but we have to use the proper symbols. So Q is used here because that is the volumetric flow rate of the exit stream. We are using Ca here because it is the concentration of A in the exit stream, and delta T as usual. So this also has dimensions of moles of A. So that's fine. So this is moles of A that has left the system during the time interval delta T. Now the reaction term, right? So the reaction rate is minus Ra. So that is in moles of A per meter cube per minute. That is the rate of the reaction. And in this particular case, because we have assumed first order reaction, minus Ra is equal to Kca. But in general, how do we get moles of A? You multiply the reaction rate with V, that means with meter cube, and then you multiply it with delta T time, right? Delta T, which is going to be in minutes. So now minute cancels with minute, meter cube cancels with meter cube, leaving you with moles of A. So the rate of disappearance of A is going to be with a negative sign because A gets converted into B and A is destroyed. Therefore, its inventory will go down, right? That's like an expenditure of A. So negative sign. This is the rate of the reaction, Kca, multiplied by the reactor volume, multiplied by time over which this reaction takes place, our time duration that we have observed the system. So in time interval delta t, this much amount of A gets converted into B. So please note we have used Ca because that is what is the reactor condition, what is inside the reactor. The concentration is Ca. Therefore, in the reaction term, we have to use Kca. So I'll just clear up all my ink work so that you understand that this is the equation. And once you have this, then it's the same thing. Divide throughout by delta T. Okay, so when you divide throughout by delta T and you take the limit as delta T tends to 0, what you have is you will have on the left hand side, if you divide throughout by delta T, you're going to have VCA T plus delta T minus VCA at T divided by delta T. So I'm dividing throughout by delta T. So this is what happens on the left side. On the right hand side, you will have QCAF minus QCA minus KCAV. So please note that the constitutive relationship minus RA is equal to KCA has been used in this mass balance equation for species A. So this is how we build constitutive relationships. This is what we get when we divide throughout by delta T, and now we take delta T tends to 0, so this will become d by d time of VCA. That is going to be equal to QCAF minus QCA minus KCAV. And since V is constant because of our assumption, we can write V dCA by dt is equal to QCAF minus QCA minus KCAV. Right? So this is the equation we can write for the system. Now, CA is the state variable because it is associated with d by dt. The system parameter is the reaction rate constant K. You can also consider V as the system parameter or the design parameter. In fact, when you do a course in reaction engineering or chemical reaction kinetics, one of the jobs that you need to do is to find out what is the volume of the reactor that is needed to convert A from CAF to CA. So the feed concentration will be given, the outlet concentration required will be given, and then you would be asked to find out what would be the volume of the reactor vessel. That's a design problem. So you'll be given Q, you'll be given K, the reaction rate constant, and if it is a first order reaction, at steady state you have QCAF minus QCA minus KCAV is equal to 0. Right? And then you can find out the value of V given what is the feed concentration, what's the volumetric flow rate, and what is the expected value of the outlet concentration. All right, or what is the percentage conversion you want, how much percent of A in the feed that you want to convert. And given the reaction rate constant, you should be able to find out V. You can do the same analysis for other order reactions. This is first order reaction, but you can do it for second order reaction or more complex kinetics. So what I want to say as a final note is that system comprises of two chemical species A and B. You can therefore write only two independent mass balances. You can write it for species A and species B, or you can write the overall balance and one component balance either for species A or B. And this is what we adopted here. We wrote the overall balance by saying the inlet flow rate is equal to the outlet flow rate, assuming constant density and so on. Once that was done, we had to write only one component balance. If we had to write the species balance for B, species B, then we have an equation of this type, V dCB by dt. Try to derive this. Is going to be equal to 0 because the inlet stream has no B. Inlet stream is pure A. Therefore, it has no B. You can write minus Q times CB minus, actually it should be plus because B is formed. And for every mole of A that is destroyed, 1 mole of B is formed because the stoichiometry is A goes to B. Therefore, you can write plus KCA times V. So the plus sign is because we are writing it for species B, which is a product species, and this gets formed. Therefore, you should have plus. For A, it was minus because A was destroyed due to the reaction. Now, the reaction rate is KCA, and stoichiometry that we have assumed is A goes to B. So for every mole of A that gets destroyed, 1 mole of B gets formed. So this will be the amount of B that's formed during the time interval delta T that we observed the system, and that you have to multiply it with V like we did here. So you will get an equation like this if you write a species balance for B. So Try to see if that makes sense to you. Thank you.